So I thought I'd take a deeper look at this display board that I came up in a separate video I did, kind of looking at the haul from over the weekend. It became very intriguing to me because under the black paint here, it's Sega. I mean, it's the Sega logo. GD1210, I've done a bunch of Googling and search, and I cannot figure out what this board came out of. I'd be curious to know. I believe this is probably the date code, 4th week of 81 perhaps, and maybe a serial number. It's hard to say for sure. 81 would probably be about right for this. These are 7-segment displays, obviously, with a decimal point. If you count, there's 18 total displays. So it runs from LED 1 down here to LED 18. So there's 18 total displays. And if we talk quickly about how 7-segment displays look internally, we've got our display with our segments and our decimal point, and the segments are labeled A, B, C, D, E, F, and G here in the middle, and the decimal point. What you typically have electrically, and I don't know if these are common cathode or common anode, but I'll just draw them in some fashion here. 5, 6, 7. That should all be in frame. You've got 8 total LEDs inside, one for each of the 7 segments and one for the decimal point. And typically, one side will be common and come out to a pin on the device. And then each of these will come to their own pin on the device. I'm not drawing those really well. And so we've got 8 total LEDs, so we've got 8 pins that represent each one of the segments. This LED might be segment A, this one B, this one C, D, E, F, G, and the decimal point down here. And to light it up, of course, you're going to put a positive voltage here, and you're going to ground whatever pins you need here to light up those LEDs. In a multiplex display, you would have another 7-segment display. And I'm not going to be able to draw this really well, but I'll draw it like this. Again with a common pin. And in multiplex, what you're doing is you're taking this pin and connecting it to here, this pin and connecting it to here. I'll draw one more LED in. This pin and connecting it to here, and of course, etc. through all of these. And so what you're doing is you're putting the bit pattern here that you want on that display by taking these low and then putting a positive voltage here, and whatever those segments you want lit light up. Then you take this pin back low, you change the bits to be the segments you want lit here, and then you put the positive voltage on here. And so by multiplexing, you're walking through each display one at a time, putting the bit pattern to be displayed. And then in this example, taking the common pin on one of the displays high, and you're driving through them all. Now, I've talked you through this part of this because what's so curious to me is there's 18 total LEDs. So we'd expect there to be 18 common pins, each one of these having a common pin. And looking at this, just from what I can see on the top silk screen, it looks like I have a common pin here that doesn't go anyplace else. I have a common pin here for display 2, a common pin for display 3. We get all the way to display 10 here, a common pin. Now I haven't checked this yet, but I'm assuming there's going to be a common pin for 11, and it's right here, it looks like. No, maybe not. What does that one shoot off to? Anyhow, there's going to be a common pin for each one of these. There's 18 displays, that's going to require 18 pins. Well, if you count the number of contacts along the board here, there's 23 total contacts. Oh, the pink bled through. There's 23 total pins or contacts on this printed circuit board. So if we say there's 18 devices and each one has its own select pin, as we talked about down here, and we subtract those 18 pins out, we get 5 remaining. Well, now wait a minute. For a 7-segment display, there's going to be 7 multiplex pins, and if you're using the decimal point 8, there's not enough pins here then for this just to be multiplexed in the simplest way, which is odd. I would expect there to be more like 30 pins, 23 or 18. Expected to be 25 pins at a minimum, 18, one common for each, and then 7 more representing the segments. So there would be 25 pins, yet there's only really 23 pins on here. Or is it just that this is labeled funny? I'm trusting what I'm seeing in the silk screen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. There really are just 23 external connections coming off the board. And the question then becomes, how was this board meant to work? Looking at the number of tracks, there's 3 pins that seem to be pretty common here. So the whole thing's really kind of weird. It makes me wonder if these devices actually have a built-in latch and decoder, and so you're sending a 4-bit BCT value to them and latching it in. And so if 18 with 23 pins, if 18 was the latches, that would leave me with 5 pins remaining. I would need 4 bits in BCD to get from 0 to 9. So if we took 4 away from that, there's still 1 pin left. But if these have internal latches and decoders, they require both power and a ground pin. So again, I'm still short a pin what I think I'd need. I need 18 latch pins, 4 BCD pins, a VCC pin, and a VSS pin, and that gets me to 18, 22, 23, 24 total pins. So again, it doesn't work. I'm kind of mystified about how this is being managed. It's possible that it's Charlie-plexed in some way. Charlie-plex is you'd have to Google it, as a way of getting more effective combinations in a multiplexing scheme than the number of pins you have. So I just don't know. I mean, I find this board fascinating. Group 1, then a group of 2, a group of 3, a group of 4, and a group of 5. That's just interesting. So what I think I'm going to do next here, move some of this out of the way, is remove one of the displays from the board so I can see if I can get a part number off of it. So let me get to the soldering gun out here. I was going to actually do this before I started the video and forgot, so it'll be warmed up. And pull one of the displays off. I don't want to, at this point, just scrap the board to add the 7-segment displays to my collection of 7-segment displays. There might be actually a bit of significance to this board. You know, it's again, I don't know how well this shows up, but the Sega here that's just been, you know, with a Sharpie covered over. So actually, I got to turn this thing on if I expect it to heat up. So we'll give this thing a couple of seconds here to warm up. You know, it's just really difficult looking at this to figure out how this is being driven. I just don't see enough pins in either case, and until I can determine what the part number is, and from there we can figure out what the device pinout is, from there then I may end up just actually reverse engineering a schematic out of this, just because I find it really interesting. This probably isn't warmed up enough yet. Well, it does heat up really quick, which is nice. Let me make sure I've got a firm amount of solder there. Where's the... it is drawing a nice vacuum. So let's just pick a random victim here and unsoldering it. Trying to be careful not to raise the tracers. Some of the pins are slightly bent over, as they did to hold them in place while they soldered them. I don't know that that one completely unsoldered. I'm actually going to fire up the other pencil here and use it to straighten up a couple of the pins here. I got to swap the tip out on that before I remove the solder. I'm going to use my very expensive JBC soldering pencil here as a wedge. Don't necessarily recommend you do this, but I do all kinds of things I don't recommend, so I want those pins to kind of be a little more upright. Especially that one there. If I can get under it, which I really don't seem to be able to. I may have to use a different method to desolder that last pin. So they're all loose but one pin. I believe they're all loose. I guess I will just kind of do what I shouldn't be doing here and see if I can get that pin to look up straight. And it's not going to do it like that. Nope. Get the solder to flow if I can. There, it flexed up. Okay, that's better. Let's see if we have him sufficiently loose to come out. I can see through all of the vias there, so I know all the pins are released. They all rock. There we go. So it's an NEC SN713B. I don't know what that part is offhand. The next step here will be I'll pause recording, go down and look at data sheet up for this, and come back and we'll look at the data sheet and see if we can figure out how this works. So didn't find much data sheet wise, but did find this page that looks to be the same device. Actually somebody selling these on eBay, new old stock, and this was with what they had on eBay. Did not find a data book, but as this shows, it's a common anode display. So it's just a standard 7-segment display, common anode, and then a connection for each of the, the LEDs as we kind of drew before. It tells me that pin 9 and 4 are tied together and are the common anode pins. So what I would expect to see, and that's what we saw here, that's pin 9, so that's the common for that device. So we know that these, we get all the way over to position 8 here. That's the common for him. Now it becomes a little bit more difficult to figure out. Let's get to the common for this guy and see if we can find where it's attached. And this is where it's becoming interesting. So the common anode from device 9 is in parallel to device 18. That then begs the question, that's common. I'm actually getting the segment to light up there slightly. Okay, so that explains a whole bunch right there. If his common is to here, hopefully I'm not sticking my head in the way here. So where's the common for him? Oops, it would help if I actually maintain contact. Interesting, I'm not finding it. There it is. So he's common with him. He's common with him. That's really bizarre. Let's get a piece of paper out here and start to create a picture of what we're seeing here. So we have 5, 4, 3, 2, 5, 4, 3, 2, and 3. We have a pin 1, 2, 3, 4, 5, 6, 7, 8. I'm only going to label so far 1, 2, 3, 4, 5. And that represents the first 8 pins along here. And we know just looking at this directly, these first 8 LEDs, the common pin, is tied to those contact points. But what we've discovered here is this is a form of some kind of perhaps Charlie plexing. I want you to sit flush, please. So if we go to the common here, the common on here goes to pin 1. Pin 2, which I expect to see there. 3 that I expect to see there. 4 there. 5 there. So what I'm drawing here is this pin 5 here is the same as this pin 5 over here. It's the pin 5 in the header strip. So the question is, where are these up here multiplexed to? 1, 2, 3, 4, 5, 6. I know I found that earlier. We'll go all the way to this guy right here and figure out the pin he's common on. So he's common off of 8. Seven and 6. And I've missed a guy here, which is 5, 6, 7, 8. And he is to pin 9. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. How can that be? 9, 1, 2, 3, 4, 5, 6, 7, 8. 9 plus 8 is only 17. So what have I got wrong here? There's 18 total LEDs. He loops back to 1, 2, and 3, 4, and 5, 6, 7, 8. 6, 7, 8. 5, 4, 3, 2, 3. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. What have I drawn wrong here? 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Is there actually 17 LEDs? 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, I'm taking where it says LED 18 here is meaning there's 18 displays. 9, 10, 11, 12, 13, 14, 15, 16. There's actually only 17 displays, so LED 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Stupid. I took one off and didn't draw it here. Hopefully you're smarter than I am and caught that. And his common, we're guessing, is going to go to 6 when it does. Did I do this wrong? And it says his common must really be 7, and I just counted wrong here. Okay, that was kind of dumb. This goes to 6, this goes to 7, this goes to 8. So there's two. So these two displays, this guy and this guy, are addressed at the same time. So we've accounted for 9 of the total pins. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 14 pins left. Oh, okay, I now understand what they've done. So I can explain this. So let me talk you through and see if you can come to the same conclusion I did. We have 23 total pins to connect. We know we have 9 of them consumed. There's 9 that are common to these, and the same 9 are common here. So if we subtract 9 from the 23, we get 14. And there's the big clue right there, what's going on here. So we talked about these being 7-segment displays. So we need 7 pins. So what they've done is they've taken, I'm guessing this group right here, 1, 2, 3, 4, 5, 6, 7. I'm guessing this group right here represent the 7 for the for the segments on these. And this block of 1, 2, 3, 4, 5, 6, 7 represents the common on these. So what they've done here, I don't know if I can draw this or not in a way that'll make sense. Is they have two banks of 9. So I'm going to call this 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to make those A, 1A, 2A, 3A to 9A. And I'm going to make this 1B, 2B, 3B to 9B. The common anode pin on these are connected together. The common anodes on these are brought together. The common anode on these are brought together. And the common anode on these are brought together. And these are coming out, they've got this on frame, to the pins that we determined were pin 1, 2, 3, and this would end up being 9, the common anode. And then what they've done is they've taken the segment leads, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. And they have put them together this way. And one bank of these is going to be pin 17 to 23. And the other bank is going to be pin 16, 2, 3, 4, 5, 6 to 10. So that's how this works. They are putting the bit pattern for this display on these set of pins here. They are putting the bit pattern for this display on this set of pins here, and then taking the common pin, these are common anode, low to light them up. Then they're putting out the bit pattern for this one, and I believe this one, and taking, actually I've done this one, it would be this one, these two on this common pin here, then put out the bit pattern for these two and take his common low, the bit pattern for those and take it low, and that's how the multiplexing works, and that's how we got to 23 pins. So we have 23 pins, we have 2 banks of 9, so we can take 9 away for the 2 banks, leaves us 14. We can subtract 7 for the set of the bit pattern up here, bit pattern bank A. It gets us 7 left, and that's the bit pattern for bank B. So I think you can see what I went through here trying to understand this, that as we went back, what we originally kind of drew out here was 23 pins. If there was if the common pin for each one was brought out individually, there'd only be 5 pins left, and that's not enough to drive 7 segments. If they were some kind of a smarter device where you fed out a 4-bit BCD value when you latched it, I was still short a pin, because in order for there to be a latch and a BCD driver built inside of the display, it needs VCC and ground, it needs power and ground. And we would again have 18 latches brought out and 4 bits for the BCD, but we wouldn't have, we have VCC, but we don't have a pin for VSS. So the 2 schemes in my head for doing this didn't click, which kind of left me intrigued, which gets us down to really this, which is kind of an interesting, there's no magic here. If I can get this to pick up and move. No real magic, but now I understand the basics of how they're wired up. Question becomes, what do I do with it? 18 of these really pretty displays are kind of nice. These displays are interesting in this form factor, and I'll show you why. Because if you take a standard 600 mil IC socket, these are actually wider than that. So I'd have to have, I think 800 0.8 sockets. But these are designed so that you can use sockets and set them side by side and get them into a dip socket. So you can set them side by side directly plugged into a dip socket rather than solder them in. I think part of why they did that in the early days is they were fairly unreliable, and it was much easier just to pop a device out of a socket. And of course, having them side by side would let you make calculator displays or whatever. But there's 18 of these guys. I don't know how many are actually good. Something we did see here, I don't know if it's showing up on camera, and I don't know if I can make it happen here again. Yes, for this guy here, the decimal point slightly lighting up there. C segment, D segment, E segment, B segment, G segment, A segment, and the F segment. So we're just barely lighting up, and I don't know that the camera is sensitive enough to pick that up, but I can forward bias these enough to actually get them off this particular meter here to light up. I don't know if this meter has actually diode test. It would probably light these up nicer. Let me switch over to diode test. And we'll see. Not really any brighter. It's forward biasing at about 1.65 volts. 1.65. I expect them all to be 1.66 to get the diode to forward bias. So old displays like this are pretty high current draw, pretty inefficient. But I can see from this, you know, just for these couple I've mucked with here, the segments have some life left to them. So I guess the question before I close the video here becomes, what do I do with this? Do I salvage these with the intent of maybe doing some kind of project with them? You know, an 18-digit calculator. You know, 18 digits, I could do GPS locations to a fair amount of precision. I just don't know. Or do I just leave the board intact and hold on to it as it is? I wish I knew what it came out of. I hate to remove the displays and basically scrap the board without knowing what it originally was in. Especially if somebody has the arcade cabinet perhaps this came out of, and they need the board, they need the displays. It'd be really nice to see this rehomed back to really the original device that it came out of. I don't know that we're going to get that lucky. I'm not going to solder him back in. Instead, I'm just going to tape him back in, just so he doesn't get lost. That way I'm limiting the amount of stress on the pins and the pads. So I don't want to lift a trace on the board. Well, I hope you found kind of the investigation of this as interesting as I did. It really, obviously, as you saw in the video, had me perplexed as to how this worked. The scheme makes perfect sense. We have the perfect number of pins for what they did. I may actually take a play at driving this board off of one of my microcontroller projects just to see it lit up and do something. Anyhow, I hope you found that entertaining, and we'll talk soon.